Hey guys, welcome back to chapter 13. In the first video, we introduced ourselves to this idea of chemical equilibrium. The next thing we're going to introduce ourselves to is something called reaction quotient. So this is going to be one way that we gauge whether or not we've hit that equilibrium mark. So are we at the point where the rate of the forward, the rate of the reverse is equal? Or are we at some point before that moment, some point after that moment? So this is just going to be a mathematical gauge of, are we at equilibrium? So reaction quotient, it's going to be denoted with a letter Q, Q for quotient. It's going to allow us to mathematically express the amounts of reactant and product during a chemical reaction at any point in the reaction. So it could be before we reached equilibrium, it could be at equilibrium, it could be we're past equilibrium, like we pushed too much into the products. So it's going to give us a point to start at to look at whether or not we are at equilibrium. So it's applied to reactions that may or may not be there. It also will help us to determine which direction equilibrium lies. Like, are we just not at equilibrium yet and we need more products to form? Or did we kind of push past equilibrium? We've got too many products and we have to kind of settle back into the reactant side. So it's going to help us to decide which way is equilibrium. How do we find it? How do we get there? Skill we're going to learn is writing kind of the equation for the reaction quotient. This is going to be the same skill that we have once we start talking about equilibrium constants. So the skill we're about to learn is something we're going to use literally the rest of the chapter, so an important skill. So here's just kind of a generic formula for a reversible reaction. So the formula is A reacts with B to produce C and D. Now the lowercase letter is a little bit confusing, but the lowercase letters in this case are going to be the coefficients. So maybe we have 2 moles of A react with 3 moles of B. So those lowercase letters are just going to indicate the coefficients. So to write the reaction quotient, our reaction quotient is denoted with the letter Q. So we're going to write that, oh, not there. That's silly. We're going to write that letter Q, and that's going to be equal to, anytime we're looking at reaction quotient or eventually equilibrium constants, we are always going to write the concentration of products over the concentration of reactants. That's going to be kind of our rhythm this chapter. When I say concentration, so you know us lazy chemists, we have ways to symbolically represent everything. When I say concentration, I symbolically represent that with brackets. So they are brackets, lazy chemists, not parentheses. So make sure we square off those brackets. The concentration of our products is going to go on the top of our fraction. So in this particular example, I'm going to take the concentration of product C, and I'm going to multiply that to the concentration of product D. So that's how we symbolically represent our products. We're going to take C times D. Now we have to acknowledge how much of C and D are being made. So we have to acknowledge those coefficients. And the way that we're going to acknowledge coefficients is they're going to be exponents above these brackets. So if there was a coefficient of 2 on the C, we would put it squared up there, okay? So we're going to denote coefficients as exponents. And then I'm going to do the same thing with my reactants. So we're going to take concentration of A raised to the power of the coefficient times the concentration of B. So this is the, I guess, formula, if you will, for reaction quotient. The values for each of these will be given. So one of the things you'll learn in this chapter is we have to have experimental data in order to do any of these math problems. So you'll be given the concentrations of the products, given the concentration of the reactants, and we just need to plug it into this formula. So here's just kind of a cleaned up version, a digital version of the exact same thing that I wrote on the screen for you. So once we have those values and we plug them in, so we have a concentration of C, we have a concentration of D, A, and B, we multiply, divide, do all the things, we'll get a number spit out for the reaction quotient, okay? That it spits out can vary from equation to equation. So the number for Q for a given reaction can vary prior to equilibrium. So if the value is one thing, that might be before equilibrium. If the value is something else, that may be past equilibrium. But that numeric value is going to mean something to us. It depends on the concentrations at that particular moment, okay? So we're kind of taking a snapshot, like, it's a way of kind of like testing, kind of a litmus test, like, are we there yet? So it's a way that we're testing. And we can test it at any point in the reaction. Okay. So let's just do a little bit of practice with this skill, as it's going to be a skill that we're going to use for the rest of the chapter. So I want to write the Q expression for the following reaction. So take a minute, pause the video and try, and then I'll catch up with you. Alrighty. So we know that our Q expression is going to be the concentration of products over the concentration of reactants. So concentration of products is going to be concentration of carbon dioxide. And then remember, we raise it to whatever that coefficient is. So I'm going to raise this to the power of 2, or I'm going to square it. Products over reactants. So I'm going to write the concentration of my reactants, carbon monoxide, raised to that coefficient, times the concentration of my oxygen. And for this one, you can put it if it helps your brain, but remember there's an implied coefficient of 1 right here, so we're raising that to the 1 power. If you want to implicitly put it in there because it helps your brain, do that, but it's not necessary, you don't have to do it. So quotient for this reaction. And then the slides just kind of click through and do the same thing for you. So here's just some more practice, so you can go ahead and pause the video, and then as I click forward, you'll see the answers right on the screen. All right. So now let's talk about what Q means and how we know where we are. Okay. So I need to introduce this idea of an equilibrium constant K. This is the value we're probably going to live in for the rest of the chapter. But for this concept, we need to understand the K value and how it relates to Q. So the equilibrium constant K is the constant when our reaction is at equilibrium. What you'll notice about the equation for K is it's exactly the same as Q. So concentration of products over concentration of reactants, with those exponents being the coefficient. Okay. When we have this, when we have a reaction at equilibrium, the ratio of products to reactants will be a constant for a given reaction at a given temperature. So this is in fact what it is called. It is a constant for a given reaction. Now, in the rest of this chapter, there may be some times that we're solving for the constant. We're trying to determine what it was. There may be some times where the constant is given to us and we have to figure something else out. But at the end of the day, it is a constant, right? It's a value, a predictable value. So how is that important as we relate this to equilibrium constant to the quotient? So remember I said the quotient is a gauge of are we at equilibrium or not? If we are at equilibrium, our reaction quotient Q, the value that we get, will be equal to the equilibrium constant K. So this is true at equilibrium. If we are not at equilibrium, if we are before equilibrium, we've flown past equilibrium, then what we will see is this Q value could possibly be bigger than K. We could see this Q value possibly less than K. So these two scenarios are not equilibrium. So these two values are not at equilibrium. Okay. So how do we know where we're at? How do we know where equilibrium lies? The next graphic I'm going to show you is kind of busy. It's a table. We're going to talk our way through it. And then I also have just kind of mathematical statements to say the same thing. Okay. So here's our graph. Let me talk you guys through this. So along the bottom, we've got concentration of reactants to products, and then products back to reactants. On the other side, from top to bottom, we've got our value that we solved for, either Q or K. So here's the big talking points. Here's the big things I want you guys to recognize. Number one, this red line right here is our equilibrium constant K for this reaction. We don't always know the target, but in this case we do. The target is the red line. This is K. This blue line is going to represent where our reaction is. So down here is kind of before we get to equilibrium. Up here is past equilibrium. So what we're going to do is we're going to use this graphic to help us understand the relationship between Q and K. So down here, below the red line, so I like this because it's below the red line, what we're going to see is that Q is less than K. We're below K, right? Q is less than K. When Q is less than K, we have not reached equilibrium yet. Where do we go to find equilibrium? Well, if we think about this arrow moving from left to right, we could think of our reactants here, our products here. So in order to get to equilibrium, this reaction is going to push up towards the products. So Q is less than K. We have not reached equilibrium yet, right? We still have too many reactants. So we need to push this reaction towards the products. to get to equilibrium. We haven't made quite enough product yet. Firstly, when we are up here, Q is greater than K. We are above that line. Q is greater than K. So we've gone past it, right? We've flown past it. So if we think about this arrow again as being on the right, reactants always being on the left, right? It's kind of always how we draw reactants, products, right, left, right. So if we think about our products being here, reactants being here, now to get to equilibrium, we're going to have to push back towards the reactants. We went past K, we went above K, we created too many products. So to settle back down into equilibrium, some of those products are going to have to push back to the reactant side. So this just gives us a good visual as to, am I pushing up towards equilibrium? Am I sliding back down to equilibrium? So here's just kind of the words of the same thing I depicted. If Q is greater than K, we have an excess products, so the reaction will proceed towards the reactants until K has been reached. If Q is less than K, we haven't quite gotten to equilibrium yet, right? We have too many reactants still. So we need to push towards the products until K is reached, up towards the products. And then we have that value in the middle. If we do the math and Q is equal to K, then we are at equilibrium, okay? So if I said K is 1.45, and then we mathematically decide Q is 1.45, that would mean we are at equilibrium, Q equals K. So those are the three scenarios we can be in. Hope you guys found this helpful. Certainly going to be at least one question, reaction quotient question on the test. So just make sure you do spend the time to understand this because we are going to add a lot more things on our plate. This is a concept that gets easily missed or forgotten about, but you certainly will see a reaction quotient question on the test. Hope you guys found this helpful.